The idea of ligand field theory is that we are combining crystal field theory with molecular orbital theory to observe how bonding and d orbital splitting is occurring in coordination compounds. So what we can do first is simply observe sigma bonding in d orbitals. So I'm not going to go through the derivation, but what happens is we come up with our reducible representation, which is A1G plus T1U plus EG. So this reducible representation is going to tell us a thing or two. First of all, you may be wondering, what orbitals do these entail? So first we can say A1G is going to be our s orbitals. Then we know that T1U is going to be our p orbitals. So that'll be px, py, and pz. EG is going to be our d orbitals, but it's not going to be all of them. It's only 2 of the d orbitals. It's going to be our dx squared minus y squared and our dz squared. So you're probably wondering what happens to the other 3 orbitals. The other 3 d orbitals are actually part of T2G, right? So this is going to be our dxy, dxz, and dyz orbitals. Now, here's the thing. We're only looking at sigma bonding, right? And sigma bonding means that the orbitals are going to interact along the bonding axis. What's the bonding axis, right? It means the orbitals are going to come to each other head on, right? Now, these 3 dxy, dxz, and dyz orbitals are not coming directly along the bond axis. They're actually between the axes. So that makes them not sigma orbitals. So what ends up happening is in this configuration, they show up as non-bonding, right? So we end up getting something, an MO diagram that kind of looks like this, okay? We are actually here, let me show this. S orbitals, we have the 1 s orbital, so you get 1. T1U, we have 3 p orbitals, so we get 3 orbitals. E.g., there's 2 d orbitals, therefore we get 2. And the T2G, dxy, dxz, dyz, we have 3. 1, 2, 3, okay? So the T2G and the EG probably sound a little bit familiar, and this is from crystal field theory, right? We said that we have our 5d orbitals, 1, 2, 3, 4, 5, and they experience this form of splitting. This is EG, T2G. These ones are triply degenerate. This is doubly degenerate. Okay, so what we can see is on the left over here is going to be the orbitals for our central metal cation. And then on the right, it's going to be the orbitals for our 6 ligands that are binding to the central metal. So on the right, we can see we have the EG orbitals, we have the T1U orbitals, and the A1G. So just to reiterate, we said the EG is our dx squared minus y squared and dz squared. T1U is going to be our p orbitals, and A1G is going to be our s orbitals. And then on the left, we also have the EG, and this time we also have the T2G, which is our other 3 d orbitals, right? So the dxy, dxz, and dyz. We have our A1G orbital and our T1U orbitals, which I already said on the over here, this is S and P orbitals. So what's going to happen is they're going to form a molecular orbital diagram that looks like this. Our A1G is going to be our lowest energy, right? So the A1G over here is going to mix with the A1G over here to form a bonding orbital. But if we're forming a bonding orbital, that means we have to form an anti-bonding orbital right over here. So these are going to connect like this. Okay, we have our A1G. Now we also know our EG, which is our two d orbitals, are also going to mix together, and we're going to get EG bonding and EG antibonding. So that's going to sit right over here, and this is going to be our EG, and then we're also going to get EG antibonding. That's going to come down over here and up here as well. And then we're also going to get our T1U, right? That's our p orbitals interacting between our 6 ligands and our central metal. So p orbitals, we have 3 p orbitals, right? We have px, py, and pz. Therefore, we're going to draw our 3. And of course, because this is a bonding orbital, we're also going to get our antibonding, which is our T1U star. T1U star, this is T1U. And that's all the way up here. We're going to bring that down. This is starting to look quite messy. I apologize. Hopefully it still makes sense though. Oops. And then last but not least, we have our T2G orbital that we haven't included yet. So we only have the T2G on the left side of the equation is one way we can think of it, right? The EG is present on both sides. T1U is present on both sides. A1G is present on both sides. They are all able to interact except for the T2G. So it's only present on the left side, and it's just going to come out to the center like this and form 2 non-bonding orbitals. These are non-bonding. And as we said, it's because of their symmetries. Their symmetries, the lobes do not lay along the bonding axis. They lay in between the axes. So therefore, we do not form sigma bonds. Instead, we form pi bonds with these, which is for later. Don't worry too much about that just yet. For now, just understand that these form non-bonding orbitals. So something we do want to notice, let me just put this in over here, is the fact that this distance is our delta naught, right? That's the energy difference for an octahedral between the T2G orbital and the EG orbital, just as we saw previously, right? With just the simple splitting. We had our EG up here, T2G down here, and this was our delta O. So this is being translated into this molecular orbital diagram, just a little bit more complicated, but hopefully this makes sense.